So now that we have introduced a little bit the topic of extreme value statistics, give you a few examples. We'll start in this second session with actual estimation methods. And so there'll be we'll see two sort of applications or two sort of groups, let's say, of estimation methods. One is related to do with maxima, and the other have to do with peak over threshold. So the maxima case is probably more related to the time series that we've seen with the volcanoes. And the peak over threshold is more related to the diamond case, so both can be treated in the same fashion. The distribution of maxima. So this is where we are entering the realm of extreme value theory. So just like in probability theory, let me put on my pointer, just like in probability theory, we're going to deal with a set of random variables that are basically realizations of samples, right? Oh, sorry, so the samples are realizations of these random variables. And so we have a set of independent random variables. For example, I've taken a sample of 100. I have a sample of 100 sample, each sample described by a random variable. The question we have is what's the statistical behavior of the maximum in that of that sample? So you could say, well, there's only one maximum. That's true. But then you can imagine if I would know the distribution of these random variables here, and I'm assuming, for example, that they're the same, then I can tell probably something about the distribution of the maximum itself. So you can also imagine, what if we have a set of samples that is repeated, say, 1,000 times, then each time I can calculate the maximum. I can actually not calculate, I can have an empirical observation of the maximum, and I can look at the distribution of all these maximas in these 1,000 samples, and that would be then that statistical behavior, but then empirically described. So clearly, the probability of something being larger than any of the samples in here is this joint distribution, which is simply, in the case of independent sampling, is simply taking the cumulative distribution of the sample and putting it to the power n. So of course, f of z is not known. It could be many distributions, and so we are interested in extreme value theory on the behavior of the distribution, this distribution here. Namely, this is function of the type of distribution, could be exponential, normal, etc. And the sample, of course, we'd like to study the distribution as that reaches infinity. And so the question is, if n goes to infinity, do we see certain characteristics behaviors appearing? Do certain distributions, like exponential normal, lead to certain extreme value distribution, and perhaps, for example, log normal, log hyperbolic lead to another type of extreme value behavior? And that's kind of interesting. If that would occur, then I can look at methods for inference. The theory of extreme values, and particularly maxima, works in the same way as the central limit theorem. So remember that in the central limit theorem, we're looking at a set of independent random variables. This is important. They're independent. They're also identically distributed, so they come from the same distribution. So once we have that, and we calculate something like, for example, any kind of sum, like an average here, and we look at what is the distribution of that average. If I standardize it, for example, I account for the sample size, and account for the mean of that sample, then as n grows, we see that the distribution of this quantity becomes essentially has a mean 0, which is because of I subtract the expected value here, and has a certain variance. And that distribution becomes normal regardless of what the distribution originally of x is. And this is illustrated in this case. For example, here I have a sample. You see here the original distribution, which is if I look only at one particular sample, and calculate that sum is here basically the sample minus the mean times 1. So I basically get the sample back, except it's centered around the mean. So I start increasing that with n. We notice that this distribution becomes more and more looking like a normal distribution. And that is essentially the central limit theorem. So it's nice that we see this kind of independence occurring from the initial distribution. There are, however, restrictions. One of the restrictions is that the mean and the variance have to exist. And so let's say you say, well, the mean and variance always exists. Not necessarily true. There are certain distributions for which there's no theoretical mean and no theoretical variance. I will introduce some of these distributions later on. So in terms of then the limit theorem for maxima, basically it's a little convoluted. It says that if the distribution of M converges, so there's no need for it to converge, but if it converges for a large N, and if there are certain normalization constants that depend on N, and some then if I look at the cumulative distribution to the power of N of that standardized value, that means this is the distribution of a maximum in a sample of size N, that if N goes to infinity, then indeed it converges to some kind of distribution G of X. And so if that's the case, then there basically, we'll see in the next slide, the result of that theory, and there's a lot of essentially math going on here, which we'll not go into. That's in the Coles book. But if that's the case, then you get to three cases, that there are three types of distributions that can occur independently of the initial distribution. That's the Gumbel distribution, the Weibull, and the Fréchet distribution. And so that limit is independent of whatever f of x is. So that reads a little bit like the central limit theorem, right? Is that now we're not focusing on some average, we're focusing on the maximum. But regardless of what we have, it seems to be converging. Now, what's very important to not forget is it only converges at infinity. That also means that our sample size will have to be infinitely large for this to apply. So you say, well, that's not the case in reality, and that's true. But it also means that it's probably after some large n, we'll see some reasonable convergence. And so this also just suggests actually, and later on and when we're going to estimate things, that we have to worry about bias, because we'll never have n equal to infinite, and so this will never get really this convergence, and there will be biases that will be associated with any of the estimation methods. And that makes a lot of sense. If you're going to estimate something that's outside of our range of observations, we really have to worry about bias. Okay, let's look at an example here. So here we're testing two distributions. We're looking at samples that are drawn from the exponential distributions and samples that are drawn from the normal distributions. And so here we notice this is the exponential distribution. Of course, we got it starts at infinity and it declines, and here we have a normal distribution. So if n is 1, then I'm just looking at their distribution. So now imagine that I take that would take 10 samples from that distribution. I'd repeat that an infinite amount of time and look at the maximum of that sample, basically, and then I will look at the distribution of those million maxima. Then I will get a new distribution, and this is for n is 10 would be then this distribution over here. Sorry about the color. It's not very clear, but it gives you an indication at least that as the color gets more darker, you will get n increasing. Same for the exponential distribution. And so then what we notice is a number of things. First of all, they seem to converge both to the same distribution. This is interesting, right? Is that regardless of the distribution type, the distribution of the maxima for this distribution is the same. So that means that there's something similar between exponential and normal distribution. And actually what we'll see later, what is similar is the tail of the distribution. Actually the upper tail here, because we're looking at maxima. Another thing that we notice is that it seems that exponential distribution converges faster. Remember, everything has to go to infinite. But even at n is 20, if we have looking at 20 samples and calculate the maximum from 20 samples, then we already get something that's reasonably close. Well, for the normal distribution to get equally close, we have to notice we have to get in a large amount of samples. So even though they converge to the same distribution, the rate of convergence is different. And so that rate of convergence is actually an indication of also the difference in tail between exponential and normal. We know that the exponential distribution, it goes faster that's that here, it drops down faster than the Gaussian distribution. And so that is not necessarily reflected in the eventual limit, but it's reflected in the convergence of that limit. So I mentioned that there were three limit cases, and these are the three cases here: the Gumbel distribution, the Fréchet distribution, and the Wild-Bull distribution. And so what we'll see a lot in the extreme value statistics is that these distributions are typical of an exponential form. And sometimes it's a double exponential, or a double exponential can also be written in a power way, or sort of the distributions can also be written as a power. And so we get varieties of these distributions. So the Wild-Bull distribution is particular for minima. It's used a lot for minima, so we're looking at x less than 0. The Fréchet distribution is often is used for maxima. Yeah, I did not talk about minima, but minima and maxima can be treated in very similar fashion. So again, a comparison, central limit theorem. We have a large amount of independent variables that, as we look at statistics from them, it becomes distributed. For the maxima, is the same. You have independent variables, and there's, however, an issue with whether or not we have convergence, and that is different. That makes these extreme value type theorems different from central limit theorems. Okay, so another way of looking at the same thing is to combine these three types into one type. And so this is called the GEV, or the generalized extreme value distribution. So in the generalized extreme value distribution, we can look at the subcases by assigning this parameter, which will be called the extreme value index, or the extreme value parameter. So we write this distribution. Remember, this is the cumulative distribution of maxima in a set, as this exponential form, and then this particular form here. Okay, so this has to be, of course, larger than 0. So we notice that if x is 0, we revert to the exponential form. We get the Gumbel distribution. When x is larger than 0, then we have what's called a Pareto type distribution. So, for example, here, this is the Gumbel distribution, is the green one. Then the Pareto type one is when psi is positive. So you notice that you get the blue one, which is a very fat tail. And then we have the Gumbel distribution, which has actually an upper bound, so it stops somewhere, and so that point can be estimated. Yeah, I think that summarizes that here. Of course, you still have a mean and a standard deviation, but that's now shows that you have a single parametric form of which are three parameters, and of one parameter is really important, which is this extreme value index, because it indicates the type of distribution that's present. So estimating this extreme value index and having inference on it, for example, we can state a null hypothesis that psi is 0, and then we can see to what extent we can reject or not reject that null hypothesis given some sample that will tell us something about whether a distribution is Gumbel or not. Another type of statistical analysis could be stating a null hypothesis where we say that psi is positive, and so then we'll try to reject that hypothesis, etc. And so that will tell us something about the nature of the tail, and that's going to be very important. Obviously, whether we have a red type, a green type, or a blue type of distribution.
Okay, so now that we have a theoretical model for maxima, we can start looking at some data and fitting some distributions. In other words, fitting the three parameters that we saw in the previous slide, and particularly the extreme value index psi. So when you're dealing with maxima, then obviously we have to make blocks of data, because if you have a data set, there's only one maximum. So in order to do any statistical model, you have to create replicates, various samples of maxima. And so one way to do that is to block the data into parts and then take the maximum of each part. So that works really well when we're dealing with time series, such as the volcano examples, where we could block everything into, say, 5 years or 10 years or 100 years and look at the maximum within each one of those blocks of different size. So in order to formulate that a little bit, we will introduce some nomenclature, which is the return level or value and the return period t. So in essence, and probably the one that you're familiar with is this statement here, is that If t is large, then this return level is stating that basically that stating that x is exceeded once in so many years. So you're probably familiar, for example, with the 100-year flood and the 500-year hurricane, etc. So that's basically this return value. So that there's a value, the 500-year, the magnitude of some hurricane, and its return period every some 500 years. So this x of t is essentially an amplitude as function of rareness. So in distributional terms, this is essentially a quantile function. And just to remind you a little bit about the quantile function, so if I have a distribution function, f of xp, so this is a cumulative distribution function, associated with some extreme quantile 1 minus p. So normally we say p, but because we're dealing with extremes, we're looking at 1 minus p. Then I can invert this function, right? I can say x is the inverse of f, and the argument will be 1 minus p. So that's the quantile function. So the return period within this context is simply 1 over p. So for example, if t is measured in terms of a year, then x is a threshold, right? Because the quantile function is something that measures a threshold above which some extreme event is going to occur with some probability. So this probability now is reflected in 1 over p rather than p. So for example, if t is measured in years, then x is a threshold that's exceeded in 1 year with some probability 1 over t. Okay, if it all sounds a little bit confusing in terms of the words, let's just simply do a simple example. So I'll be talking about this rainfall data set I found online. It's in Switzerland. Doesn't really matter. So we're talking about daily rainfall, and so we're looking at quantifying return periods. So for example, what if I say the following statement, that the t is 5-year return value, right? This is going to be a value. This is going to be a period, is 70 millimeters. So that's, remember that a centimeter or 2.5 centimeter is 1 inch. So what does that mean? That means simply that a rainfall amount of 70 millimeters, this is now the threshold, is exceeded in 1 year with a probability of 20%. And so this 20% relates to this t is 5, so 1 over 5 is 20%. The other way of saying the same thing is saying, or using that in the same, not the same thing, but using our example in this different context. Imagine that we have a very large rainfall occurring at some particular year. Say in 1954, we observed a rainfall amount in that day of 89.6 millimeters. And so the rainfall occurred at this as a return period of 15 years. That means essentially that such an event or larger is expected to occur every 15 years. That doesn't mean it occurs every 15 years. It is an average aggregated over all the data set. What's the problem with return levels and periods, etc.? And we see this in practice when people talk about this, even people, let's say, people who are not statisticians. Suppose that I have an extreme event, right? I suppose that in 2005, in August, I observe 177 millimeters. That's a significant amount of rainfall, evidently. And so imagine that I've never, ever seen this in my entire record. So imagine that my record goes back to 1905, 1901. So the first problem, of course, I have is that the empirical return period, this is what we empirically observe, right? This is not an average. This is whatever we observe, not a model average. It's whatever we observe. So if I haven't observed it in 2004, I have no data there because I have not observed it. The previous amount was 150. So that means that now in 2005, I have 105 years of record, that the return period for that is 105. That would be the empirical return period. But this kind of data messes everything up in terms of empirical return periods. For example, it replaces, first of all, the existing maximum, which was 150. That means that the return period of 150 would drop down from 104 to 53. Etc. Another problem, of course, is that you can get big jumps in return periods. So all of a sudden, You go from 35 to 27. You may have jumps of return periods when discrete amounts of rainfall falls. For example, 132 millimeter was an observed high, and 133 was an observed high. So you get these big jumps in your data, and that's, you know, for modeling, or that's always will be a problem. So these empirical return periods are not very robust. So we have to look at these things in a very different fashion. Okay, so what is a better way of representing all this return level plots and these return values versus return period? So then we introduce here the return level plot. So here's the extreme value distribution in its general form. So it's a generalized extreme value distribution. So it's a cumulative distribution. So that means that the argument x is a value, and the return of that function is a probability p. So remember that that return level is not p, it's 1 over p. So what I will do here now is to calculate the quantile function, right? Because in previous slide we showed that, or previous discussion we showed that x is the return value that occurs with some 1 over p, which is the return period. This is the return period. So what I can do is I can take the logarithm of all this. So the logarithm of the exponent becomes then this function, and then you have a logarithm of p. So and then also I do 1 minus such that I get this nice form. So now I see here that the return value is a function of all this here. And so remember, this p is related to the return period here, which is 1 over p. So depending on whether you have a Gumbel distribution or the other form where xi is not 0, you get this kind of form here. So we notice here basically that there's a log minus log argument, and we'll see this return also in the next sessions. This log of minus log is going to return a lot. That kind of makes sense because if you're dealing with extremes, then we like to look at the log, and sometimes we need to look at the double log if we want to look at something that becomes eventually linear. So for example, if I take y of p minus the log, then this is just a function of p again. Then if I plug that in here, then I see that x of p is a linear function of log of p, or log of y, sorry. And so if I then plot log of y versus the quantile, the observations, then I will get, for the Gumbel distribution, I get a linear function here. So that's what we get here. And so if the extreme value index is positive, then I'll get something that's increasing faster. If extreme value index is negative, then I will get something that increases slower. So as a lesser tail, I get lower quantiles with respect to the Gumbel distribution. Okay, so now we can start then building the empirical return level plot. So that would be plotting the data now in that same framework. So the easiest way to look at this is when starting from the Gumbel distribution. So remember, from the Gumbel distribution, which is this distribution, we have observed a linear relationship between x of p and log of minus log p. So this is that return level, that yp value. So we know that the return level, right, is t of x is related to the cumulative extreme value distribution. This is the definition of return level, which is 1 over 1 minus p. So if I have now observed a number of maxima and rank these maxima from the smallest maximum to some other maximum, then I can plot the rank essentially of that data point, which is 1 divided, so that's t. So p is now estimated by the rank. So if I have, for example, if I have n data points, then I can observe essentially n ranks, and I can plot that. I want to also deal with the n here. That means I don't want n divided by n or something like that. So I take the rank divided by n plus 1. So that replaces this p here. This is quite commonly done when calculating quantile plots. So that would be then the theoretical, and this would be then the observed, and that would be then this plot of these dots here. And so this is now for, I think, the 1-day rainfall, not for the 2-day rainfall. So that means that this is no longer the biggest. So, and so that's nice. Now we have T versus that, and also we have a theoretical model for that, which is this line that we can start fitting. Okay, so now imagine we have fitted some theoretical model or some distribution, and now not the Gumbel distribution necessarily, but the distribution that involved the Xi. The fitting I'll talk a little bit in the next slide. So what does this now all mean? Okay, so for example, let's take a couple of examples. Let's say here, let's look again at our extreme event here in 2005. So for that value, I can now calculate the theoretical, not just the empirical, but I can calculate the theoretical return period. So this would be now, that will be now at the 46. Imagine this is around 46 here, that this amount of rainfall has a return period of 46 years. So if I now add data to this, then this modeled return period would not jump in the same fashion as would the empirical levels, and it gives me much more robust, essentially a robust idea of what the return period is of 46 years as I get more data. The other thing that we can start looking at, I can also look at, say, what's the 10-year return value? What do I expect on average to happen every 10 years? Well, that is this value here. So now we're going the opposite way, and I find that this is 82 millimeters. But what's also very nice, of course, is I can now start doing extrapolation, which is, for example, I can look at what's the 200-year return value, and I just look up the 200-year return value and find that it's 145 millimeters. So now you can start modeling or using this information, whatever context you may have. For example, it could be in rainfall, of course, is important for agriculture, or for planning, or flooding is important for mitigating hazards, etc. So these are very important plots, evidently, in practical situations. So parameter estimation, in this class, I'm not going to talk too much about these things, estimation, regression, things like that. I mean, those are things you could find in more classical statistical books. And also, I think as a practitioner, when you're going to use this, it's good to be aware that there are methods, but you don't have to know the derivation of all these methods in order to apply this. And I think in this class, I really want to focus on the application and not too much be distracted with theory of estimation. There are method of moments, which is, I'm not going to talk about that either. These are similar to the method of moments, such as mean, standard deviation, skewness, etc., that we have in the more center limit theorem arena. And of course, there's also a method of maximum likelihood, so maximizing a likelihood. And of course, with the Gumbel distribution, we'll end up with the profile likelihood, and etc., etc. And so once we've done estimation, we have essentially a bunch of parameters and a value of Xi. Something that I will talk about not here, but later on in the next session about peak over threshold methods is that obviously you're not going to use all the data simply because we have to worry about, remember that the extreme value distribution, in order this distribution is only a distribution in the limit as n goes to infinity. And so we don't have that n goes to infinity. And also when we are extrapolating, we're not so much interested in what happens over here. So certainly in low values. Actually, the low values, their data may not be maybe biased possibly, and so there may be issues with that. So we have to somehow decide where to stop. And I think in the next presentation or the next session, I will talk a little bit about where should we start essentially with our fitting. And so here you get the fitting result. It doesn't look substantially different. And we also notice that the Xi value is low. So it's possible if you would do a hypothesis test that the Gumbel distribution cannot be rejected as a possible model. We can also look at confidence limits. Here, obviously, and this is something I do like to emphasize, is that, of course, all the methods here have to be parametric methods. There are no non-parametric methods or they're difficult to apply non-parametric methods to these cases simply because we're doing extrapolation. So in extrapolation, we can't just rely on data to tell us something about what happens in terms of extremes. We have to fit parametric functions. And so we can use, for example, then a parametric bootstrap, which means drawing samples from this from the fitted distributions and re-estimating, and then getting some kind of a quantile procedure. What we typically notice, of course, is that the uncertainty or the confidence is less towards the high than towards the low. And that's logical. Again, it's more difficult to estimate extremes than it is to estimate the middle of the distribution. So we typically get asymmetric confidence interval. Okay, so yeah, so a couple notes on the assumptions is that first of all, this idea of IID, this independent and identically distributed data. So that happens a lot in statistics, and so be careful what that really means. It's often stated a little bit casually. In this case, it would require absence of course, trends and periodicity. There has to be some form of stationarity in this population, and so if you think about extending or modeling of extremes in the presence of trends, future trends, then we'll have to deal with these trends separately, and often these trends could come from physical modeling and not from the data. So these trends would have to be deduced from physical models, and then the residual can be used, can then be modeled through these extreme value distributions. No serial and spatial correlation, of course, that's the independent part. That is okay usually with maxima. It's usually the case that as you increase your threshold, your return periods, then of course these events become rare and rare, and so less correlated. That's typically the case for earthquakes, but it may not be always the case. There may be actually spatial correlation in the extremes. So as I mentioned, the assumption of the asymptotic assumption of n goes to infinity, which means basically getting large blocks within which you can look at maximums. So if you get small blocks, then the asymptotic limit does not apply, and so we have to worry about the fitting in that procedure. So basically, there's this trade-off that exists, right? That we're not that used to in central limit theorem kind of methods. Is that the biases that may occur if you use too small blocks, and the large sampling errors that may occur when you have very few data when you look considering very large blocks. Okay, summary. We derived the generalized extreme value distribution as a reflection of the theoretical distribution of maxima. This is a theoretical result. It comes from a limit theorem that's different from the central limit theorem. To get this maxima data, we have to do blocking. We have to look at periods within which things are observed. We discussed the notion of return values and return periods that can be visualized in quantile plots, in which then also theoretical models can be visualized and fitted, from which then extrapolations can be done.